Hi, everyone. Good talk to follow. So like Jim said, I actually didn't realize that I was part of the chip section either. So my talk isn't specifically about chips, but it is about running on a lot of chips, specifically running some DL applications on the Summit Supercomputer. So a bit about me. I'm not a VP or a management guy at NVIDIA. I'm just an engineer. I joined NVIDIA in 2017 in their dev tech group. My background is actually in computational fluid dynamics, not data science or computer science. So some of you might refer to that as scientific computing or high-performance computing. And I guess maybe the reason I'm here and what I'm talking about today is that I was part of this Gordon Bell Prize-winning effort that a couple of talks earlier, like Francois mentioned, this climate simulation DL network on the Summit Supercomputer that won the Gordon Bell a couple of years ago, running on 27,000 GPUs. So this effort from a year and a half is going to be a bit central to this talk. What I want to do is compare the software stack that was involved in that effort a year and a half ago to recent efforts on Summit and just kind of give you the story of how that software stack has evolved to really enable people to easily scale out these data parallel workloads. So this slide is about this convergence of HPC and DL. So people talk about this a lot, HPC plus DL or HPC plus AI. The point of this slide is that the line between traditional HPC and DL are blurring, and both sides of this, both fields are benefiting from this trend. So HPC applications tend to generate a lot of data. DL is providing a benefit for them to, providing a path for them to do better and more advanced data analytics. So they use a lot of DL to post-process their data. And DL applications have been growing in scale to reduce iteration time, train larger models, improve productivity. So HPC has been scaling out workloads for decades. So a lot of DL practitioners have been leveraging that experience in order to more efficiently scale out their deep learning workloads to multiple multi-node systems. So a brief comparison of HPC workloads versus DL workloads. So HPC workloads typically are often domain-specific or even problem-specific code, typically statically scheduled. Because they're usually this custom code for this problem, they have handcrafted communication patterns over the networks for high parallel efficiency. And they're typically run on these HPC computing installations that are tightly interconnected nodes with high-performance networking. Basically, the systems are designed to operate as one massive computer. DL workloads are a little bit different. People that do DL are typically users of frameworks. And frameworks are very high productivity and very broad, often with graph-based schedulers that are typically non-deterministic. Parallel distribution strategies for these users of the frameworks typically are left to the framework developers or plugin developers themselves. So these users aren't writing their own communication. They're just relying on what's already available in the framework for them. And typically, DL workloads are run on the cloud or on-prem systems. So cloud systems are typically different than HPC systems in the fact that they're not as tightly interconnected. But on-prem systems are starting to look a lot more like HPC systems. But before I talk about the Gordon Bell effort bit, I did want to give a background on some of the important software components that we use for that effort, just in order to give a little bit of background of this talk and motivate what I'm going to talk about. So one of the major software components that we use for Gordon Bell is Horovod, which is a framework for distributed deep learning. Horovod was originally developed by Uber, is now as part of the Linux Foundation for AI. It's an incubating project. It's used extensively at NVIDIA for distributed DL training. It's simple, very few modifications to existing single worker scripts for parallelism. It's framework agnostic, so it actually can work with TensorFlow, PyTorch, MXNet, Keras, and its performance. So Horovod can actually take advantage of already existing high-performance communication libraries in HPC, like MPI, or Nickel from NVIDIA, which I'll talk about in a few more slides. I'll skip this bit here. So one of the major challenges of Horovod, though, is that it has to deal with this out-of-order scheduling from these frameworks. So like I said earlier, frameworks typically use a graph-based scheduler. So when you're running on multiple processes of these frameworks, you're not guaranteed to have frameworks schedule all reduce or collective communication operations in the same order. So Horovod has to do a lot of work to figure out when I have all these workers and these sets of tensors, it needs to coordinate and figure out which of these tensors are common across these workers and issue commands to actually do the communication over the network. The framework agnostic design of Horvath is also a blessing and a curse. So the framework agnostic design is a blessing because if you implement an improvement in Horvath for one framework, you might benefit all the ones that it supports. But the framework agnosticism also leads to a lack of deep integration in any particular framework, which limits the amount of actionable information you have for advanced decision making. So how does Horvath deal with out-of-order execution? So the core design of Horvath relies on this control coordination layer, which basically runs and processes requests for incoming tensors from all workers, and uses this logic to determine what tensors are common across all workers and what collectives perform and when. It uses this single coordinator rank design where everybody sends requests to rank 0. In this case, the coordinator. Rank 0 does some processing, eventually sends out some other signaling message to tell everybody else to do these all reduces. This coordinator loop is also very dynamic. So it just runs in a background thread at a fixed tick cycle, checking for tensors, just repeatedly forever until from the start to the end of the job. And the actual collective operations themselves occur in what we call the data plane with MPI nickel or glue. But the best way to really describe how this works, and bear with me here, I'm pointing this out because this is a major thing that we had to improve for Summit, is this diagram here. So what I'm showing is 4 worker ranks. The top is this kind of control coordination plane. The bottom is this data plane. And so how Horvath works is basically during training, at some cycle, some tensors will be ready to be all reduced on some workers. So in this case, these tensors are shown by these squares, A, B, and C. And so what happens is these workers, when they have a tensor, they actually create this metadata message object that gets gathered onto rank 0. Rank 0 then records these messages into this so-called message table. So rank 0 is the only one that is aware of this. It checks to see if any single tensor has a full set of messages. If it doesn't, it moves on. Nothing happens. On the next cycle, maybe some more tensors will show up. They do the same thing again. All these messages are gathered to rank 0. Rank 0 records them in this table. But in this case, rank 0 sees all the messages for A are ready. So then it goes ahead and broadcasts a response object to tell everybody else, hey, tensor A is ready to go. Let's all do this with all reduce. So it could be all reduce with nickel or MPI. And watch, rinse, repeat. So now all the tensors come in, gather. This time rank 0 sees that multiple tensors are ready to go. It does something called tensor fusion, where it tells everybody, hey, these 2 tensors can actually be packed together. Go ahead and do a fused all reduce for efficiency. So we're going to go back to that earlier, so hopefully you can remember that sequence of events. And what I mentioned is that Horvath can take advantage of very high-performance communication libraries. One of them is Nickel, which is the NVIDIA Collective Communication Library. It's a really, really great library. It can utilize PCI Express, NVLink for inter-GPU on-node communication, but also InfiniBand and TCP/IP for multi-node. Nickel is really, really great. It has advanced topology detection for high performance. So when you start up the job, it'll actually kind of look at your topology and try to make sure that it runs communications in a really nice and optimal way for whatever system you're running on. I'm going to be talking about Nickel here during the initial Summit effort, which was mid-2018. So in mid-2018, Nickel relied mostly on ring-based communication algorithms, which were kind of a big deal back then. And the development at that time really targeted smaller scale jobs on maybe a few moderately sized clusters, maybe DGX1 or DGX2 systems. So let's talk like order 10 to order 100 GPUs, okay? So now the question is, how will the software do on a system that was not seen before, a GPU system of a size not seen before? So enter the Summit Supercomputer. So Summit is a leadership class HPC installation at Oak Ridge National Labs. It's ranked #1 on the top 500, which is a ranking of the top supercomputers in the world. It's been #1 since June 2018. So what is Summit? Summit is 4,608 nodes, each with 2 IBM Power 9 CPUs, 6 NVIDIA Volta V100 GPUs, a dual rail EDR InfiniBand on each node. So if you do the math there, Summit is over 27,000 GPUs in a single system, tightly interconnected. The peak compute of Summit, theoretical compute, is 200 petaflops double precision. but 3.3 exaops half precision, which is astounding. So one of the fun things is I was given the opportunity to run on Summit during pre-production. So this was before the system was open to the public. A few teams at some national labs got access to the system to try and really work the system and see what it could do. And so for this project, which was talked about in a few earlier talks, it was a collaboration with NERSC, where we're training a DL network to analyze a large-scale climate data set in order to segment extreme weather patterns out of the data using TensorFlow. So extreme weather patterns in this case were things like tropical cyclones or hurricanes and atmospheric rivers. And our goal was to distribute this training workload across the entire Summit supercomputer. This particular project could be characterized as a sort of scouting mission. We were part of the first set of users to have access to and run on the full system, for one, but I guess as a result of that, we were also some of the first set of users to really test some of these software pieces at that scale. So Horovod, Nickel, or TensorFlow as well. So unsurprisingly, there were issues, right? When you make a jump from software that was designed to run on 128 or 256 GPUs, and you jump up to 27,000, I mean, you're probably not going to expect it to work out of the box, and it didn't. So it turns out that Horovod's coordinator design, which I explained in the slides earlier, completely breaks down at these scales. The problem is this gathering of these messages to rank 0, this coordinator design to determine what to do, was way too expensive. So Horovod spent way too much time thinking about what to do rather than actually doing all reduces. Secondly, Nickel's ring-based algorithms at the time completely break down at these scales. So ring-based algorithms have really linear latency. So these ring algorithms have substantially reduced achieved bandwidth, at scale. And other issues that I won't be talking about here were data management on the system and also maintaining training convergence. But we took a look at the software at the time and really did a lot of work to try to get things to run and run well. And so getting over these hurdles, so for Horovod and Nickel, what we did was we introduced something that we called the Hierarchical All Reduce. Basically, the Nickel ring algorithms just didn't work. So what the Hierarchical All Reduce did was it took the Nickel ring algorithm and only ran it on each individual node, then combined that with an MPI communication across all the nodes. An MPI has a lot more advanced algorithms, so it was able to utilize trees, which had significantly reduced latency across nodes. And so the combination of these two tools really helped us improve the achieved bandwidth of the all reduce. For the control plane, we introduced something that we call the tree-based control plane. So rather than having this single coordinator rank that everybody was gathering messages to, we built up this whole tree of coordinators where everybody was sending to a parent coordinator and sending these messages up by proxy and getting these response objects back from rank 0 through proxy, which significantly improved the latency characteristics of Horovod's coordination plane. And then beyond that, beyond the communication part, we also looked at network modifications in order to use FP16 compute, just to get faster iteration times. And also, we modified the network we were using to produce finer grain segmentation masks. Some of this climate data, if you look at these atmospheric phenomena, they're really, really fine grain, lots of branching clouds and things like that. And we wanted the segmentation masks to be able to capture some of the smaller scale features. But as a result of that, by switching on FP16 compute and really improving the single GPU, single worker performance, we found that we still didn't have enough of a budget to fully overlap the communication with the computation. So we ended up having to introduce something that we called gradient lag, which was a single step lag of the gradients. So instead of doing a fully synchronous gradient update, we actually allowed us to have one additional step to give us just more time to complete this all reduce. But the results for that weren't bad. So early efforts resulted in this exascale deep learning for climate analytics paper, which won the Gordon Bell at SC. This plot on the right shows our scaling. So what we see, I'll focus on the red line here. Basically, the red line is our FP16 compute result. The solid red line is with this gradient lag enabled, and the lighter red line is without gradient lag. So what I want to point out is that we're getting pretty good scaling. In fact, there's not a dot on this plot because it was kind of the final run. We achieved 999 petaops sustained 1.13 exaop peak compute throughput of our largest job on 27,360 GPUs. But what I want to point out is, with the lag, we ended up scaling quite well. And even with the lag, we converged pretty well on the system. The picture in the bottom left actually shows one sample of the segmentation mask we generated on one set of data. But we still ended up needing that lag to get the scaling to work, which was OK. So key takeaways from this initial effort for me were the following things. One, scaling DL compute performance alone is really difficult. Not to mention other issues with like hyperparameter optimization and tuning, dealing with large batches. Obviously, at least from my experience, the software stack was just completely unprepared to handle problems at these extreme scales without significant modification and profiling and understanding from the user side. And then on the Horvath side, some improvements were integrated upstream, but some of them weren't general enough. And notably, the control plane improvements that we made were not integrated. All right, so that was Gordon Bell, mid-2018. So now my talk is going to transition into what happened over the next year and a half, right? So what did happen over the next year and a half? So a big thing that happened over the next year and a half was the introduction of the ML-perf benchmarks. Tim actually is going to be talking about ML-perf after me, so I won't spend too much time talking about it. But basically, ML-perf benchmarks provide a suite of really well-defined baselines with strict accuracy requirements, right? And what this does is it enables a more systematic approach to improving scaling performance. And by that, I mean, while these kind of one-off efforts where we run these massive scale jobs on Summit are really cool and really a nice opportunity to test out the software stack at just extreme levels, ultimately, we still want to improve the experience for the normal user. And I think ML-perf provides a really good baseline to target to systematically improve scaling performance while also maintaining the utility of these changes. So combined with a growing interest in scaling out DL just generally across the community and these benchmarks, this whole thing has been a major catalyst at NVIDIA for really focusing on improvements in our software stack for scaling out jobs. I give an example of this picture at the top is a picture of a cluster we have at NVIDIA Circe that we have that has particular focus on enabling our developers to test and develop and improve our software stack, in particular for large-scale multi-node development. So Circe itself, this DGX2H pod, is actually number 78 on the top 500. So it's like Summit's little cousin. What else happened over the next year? Nickel improved substantially. So when we used Nickel, Nickel just was not ready to go at that scale just because they didn't have a system to run on, quite frankly. So now when the Nickel developers got access to Summit, they're really smart, intelligent people, and they were able to make tremendous improvements to Nickel. So this plot on the left shows the latency characteristics of Nickel from, if it's too small to read, 96 to 24,576 GPUs. And the right is the bandwidth, same number of GPUs. Gray line is the ring-based algorithms that Nickel used to use, and the ones that we had to deal with during the Gordon Bell. And the green line shows the performance once they introduced tree-based communication algorithms, which were much more scalable. So what we see is once they introduced these trees, they were able to significantly lower latency at Summit scales and significantly increase bandwidth at Summit scales, which is awesome. And since then, this is just one thing that Nickel's improved. Since then, they've made many improvements to topology detection, their selection of communication algorithms, an automated selection of algorithms for really great performance on a variety of different types of nodes and topologies. OK, so that was Nickel. Talk about Horvath again. So as part of ML-perf ResNet 50 benchmark, NVIDIA used MXNet's framework with Horvath for distribution. And so what was cool about this, I was part of this effort. It gave me another opportunity to look into Horvath and really look into this control plane problem and fix it once and for all. The ResNet 50 benchmark for ML-perf ran on only 96 DGX2H systems, so only 1,536 GPUs, not 27,000, but still posed some unique challenges. So to hit the required ML-perf accuracy targets, it wasn't OK to just weak scale out our batch size, right? We just take the biggest batch we run on a single GPU and then scale it out over across the entire system. What we had to do is we had to limit the global batch size and strong scale the problem, which meant that at full scale, we were running pretty small per worker batch. And small local batch means faster iterations. And that means less of a budget for you to actually hide your communication, right? Which meant tighter latency requirements needed from Horvath and Nickel. So the improvements to nickel standalone gave us enough performance to meet these latency requirements. But it turned out that the Horvath control plane was getting in our way. And so we needed to improve it. So what are the problems with the control plane? Gathering messages to a single rank is a major bottleneck. Basically, all those messages somehow need to get to rank 0. This is not great, especially with increasing scale. When you think about it, the Horvath control plane design was a bit heavy-handed, right? Typical deep learning workloads process the same set of tensors every iteration. So there's no reason to constantly be sending these messages back to rank 0 to do some coordination processing, send these responses back. So the idea was, let the first iteration be slow, but then cache information that you got from rank 0 on all subsequent iterations in this response cache. What's cool about this is that this response cache not only lets us save this communication of this response, but it also provides a global enumeration of these tensors that we observe. And again, remember, Horvath doesn't control the frameworks at all. So these tensors that it observed come in at different orders, run to run. So it provides a globally consistent enumeration of these tensors on all workers, which allows us to use this lightweight, what I call bit vector reduction to signal worker readiness of particular tensors. And again, I'll show this with some images because it might be easier to explain. So again, we go back to our little diagram of Horvath here with these 4 ranks in that message table. But in this case, let's assume that all the workers went through one step and they have this response cache that they set up. And so what this response cache does, it's basically just a table that maps a tensor name to the response that it received from rank 0 in the first step and a cache bit position. That's a really simplified example. So basically here you can see A, B, and C entries on all the ranks. They don't necessarily need to be in order. So now we do the same example. In one cycle, a bunch of tensors show up. But rather than doing this thing where they're all sending these messages to rank 0 and letting rank 0 do all the thinking, they all set bits in a vector corresponding to their position in this cache. So you can see rank 0 has all 3 tensors there, so it's set 1, 1, 1. Rank 1, rank 2, rank 3, set their vectors accordingly. And we just do an all reduce bitwise AND, just a distributed set intersection. We get the result of that, and then all the workers say, OK, cool. The tensor that was associated with the first position there, which is A, is ready to go. Significantly cheaper, significantly lower latency readiness decisions in Horvath. Another improvement we made of the Horvath control plane was that this Horvath coordination logic runs greedily. And in that, I mean, when new tensors show up, you'll try and schedule as many tensors as possible per step. So it doesn't matter if it's 1 tensor or 10. If they're ready to go, it shoots them off. And the reason why that's a problem is this. So typically for more efficient network utilization, you don't want to have a lot of tiny messages sent over the network. You usually want to kind of bulk them into moderately sized chunks. But in order to keep Horvath from creating really small chunks, you need to increase the cycle time. Because if you set an arbitrarily low cycle time and have Horvath tick at a really, really quick rate, you're going to generate a lot of really, really small messages. Whereas if you set the tick rate to a really large number, Horvath's going to be operating more slowly, maybe generates fewer messages, but that just is arbitrarily introducing latency to your communication coordination. So to deal with this, we introduced a method in Horvath to group or color tensors. And the idea here is basically just to give Horvath a bit more information from the framework that it normally wouldn't have access to in order to tag these tensors and say, you cannot all reduce incomplete groups. So just because a few tensors show up in maybe one cycle, if the group is not complete, it'll wait. It'll hold that back until the full group is ready and then push it off. And so what this allows us to do is decouple the tick rate from a minimum message size. So we can enforce a minimum message size with as small a tick rate as we want. So with some of those changes, with MLPerf ResNet 50, we were able to, in the last round, train ResNet 50 on ImageNet on that system, 96 Cersei DGX2 nodes, in about 1.5 minutes, which I think is pretty cool. Basically, press enter, go get a cup of coffee, come back. You've got a trained ResNet 50 on ImageNet. But this talk is about Summit, so I wanted to kind of bring us back to Summit. And I had another opportunity to work with Oak Ridge and Uber in this collaborative effort on Summit to solve a different problem. This problem is solving an inverse problem in electron microscopy. Basically, the problem here was to take simulated electron microscopy diffraction patterns and produce this local electron density map. Right, and again, it was just training a neural network to work on all this data on Summit to produce these results. But really, the main question I wanted to ask is, could these Horvath improvements that we made in a completely different context, MXNet for MLPerf, benefit large-scale runs on Summit for this problem in a completely different framework at a completely different scale, TensorFlow? And the answer is yes, it can. So with the Horvath improvements, along with improvements in nickel, scaling DL compute performance on Summit was now recently attainable with significantly less targeted effort. So what this plot on the right shows is kind of a chronology of their scaling performance on Summit with this particular network. So the green line shows the hierarchical all reduce in Horvath that was just available at the time, kind of a remnant of the old Gordon Bell. They actually weren't getting very great scaling performance with that for their particular model. The blue line shows when they went and introduced the updated nickel with trees. So you can see nickel right out of the bat, just installing a new version of nickel gave them pretty decent performance, but it still falls off. And that's because of that control plane. And so the black and the red lines show the effect of this bit all reduce lower latency readiness checking and grouping altogether, giving them almost nearly linear scaling. So for this particular network, they were able to achieve 1.54 exaop sustained on Summit, 2.15 exaop peak with a fully synchronous gradient update. So I think that's pretty amazing. So going to conclude my talk here. So with improvements in software over the past year and a half, the ability to efficiently run large-scale data parallel deep learning workloads with out-of-the-box solutions is becoming a reality. With that being said, there are still many open problems and new territory to cover, particularly large batch convergence, scaling and applying model parallelism to more problems, and obviously a lot more. But I do think that enabling efficient computation at scale alone opens up new and exciting opportunities for a lot more research and development in deep learning. So with that said, all the software is available for you. So Horvath is an open source project. It's a growing number of contributions from many companies. It's available at horvath.ai on GitHub. Of particular relevance maybe to this audience here, the recent v0.19 release has this experimental support for this ADASUM gradient aggregation technique developed by Microsoft for improved large batch convergence. So maybe you should check that out if you're interested. And also Travis from Uber has been working on some experimental multi-node elastic training that they're targeting for support in v0.20. And then on the NVIDIA side, we do all this stuff to benefit you guys. So we release a monthly container on NGC for all the popular frameworks with GPU optimized with the best and latest changes that we make to our software. These containers are available at ngc.nvidia.com. Nickel itself is also open source, so be sure to check that out on GitHub as well. And with that, I will conclude my talk. Thank you very much.
Yes, I have a question about after you scale the machine learning, deep learning to the actual scale, so how did you handle the task failing in the scaled job?
So
after, if you handle the job failing and if you restart the job, how did you do the job task synchronization and make sure the whole job can be run in the same time?
So I'm not sure if I totally caught your question. I think you were talking about reliability, how would you deal if the job failed?
Yeah.
So for these really, really large-scale jobs, they're not going to let you run on the full cluster for a very long period of time. So actually, for most of our jobs, we didn't run into node failures during the reasonable during the time that we ran the job. But we would write out a checkpoint and then just restart from that, in smaller increments of time.
Okay. After you used some checkpoint and restart the task, and how to make sure about multiple different tasks can be keep the synchronization and be run at the same time?
I'm still not.
Yeah. You mentioned you will do some the checkpoint to make sure about the failed job can be rerun, right? And if you rerun the job, how to keep the multiple different the task can be keep the synchronization.
Well, so I mean, everybody restarts at the whole process ends and you restart it, and then the checkpoint gets broadcast to all the workers, and they just restart from an initial save state.
Okay, you will restart the work.
Yeah. So this work doesn't have anything about like fault tolerance or elastic, anything like that. Basically, this is just we ran the job and it worked.
Okay. Yep. Thank you.
Thank you.
Let's thank Josh one more time.